Oh, let's pick it up there. I paused and we'll pick it up there. I was just in the last video, I was just struggling, and it's nice that I confirmed this guy. The last thing I did is I said, well, let's put 3 in here, and I get 3 plus 1, I get 2 to the 4th, and I came down and I said, ooh, that 3 looked suspicious. So hopefully you watched the other video before this. Here I needed to subtract 1. I'll bet you caught that, and I was doomed right there. So we put 2 in. I get 2 to the 2 plus 1. That's 2 to the 3rd, 8 plus 2, 10. We have this graph confirmed, but I caught a mistake there. I actually graphed it correctly, but had it incorrect down here. So apologies, I'm sure you saw that. If you just joined this one, you may want to go back and look at, we are working on chapter review test right now. This will be the second video to that. So picked up on an error. I tried to pause and had no success with the pause. I actually stopped the program, so my apologies there that this is a little bit muddled, but it's a good continuation from where we were. Okay, one more of the sketch the graph ones. Sketch the complete graph, give domain and range both in set builder notation, interval notation, rewrite the function in piecewise form. We did that earlier. And then we have list x and y intercepts as coordinate points if they exist, provide at least 4 quality points. So I'm going to go down to my t-chart down here, and I'm going to rewrite my function. F of x is absolute value x minus 3 plus absolute value x minus 1. And pretty harmless little function as far as calculating this out by hand, but for sure, here's 2 points I want to list, because this portion of the graph is interesting around 3, and this portion of our function gets interesting around 1. So I'm going to start with those. I want to point between, and I want to point on the outsides. So again, if I looked at this on a number line, I know something interesting is going to happen at 1. I know something interesting is going to happen at 3, so I should probably test those. Everything in here is linear, so it's going to be just a connect the dots with straight lines, but we're going to want to get some intervals in between there. So test some intervals. So when x is 1, I get negative 2, which comes out as 2, plus 0, 2. When x is 3, I get 0 plus 2, absolute value 3 minus 1, 2, and I get 2. When I put in 2, see what we get here. I get negative 1, 1, plus 1, 2. So far this looks like a factory that specializes in making 2s. Let's try something to the right of 3. I'm going to put in 4. Whoops, put in 4, sorry. And I get absolute value of 4 minus 1, 1, plus absolute value of 4 minus 1, 3. 4 minus 3, 1, 4 minus 1, 3. And I get 4. And I'm going to put something into the left of 1, for instance 0. And I get negative 3 becomes positive 3. Negative 1 becomes positive 1. I get 4. So let's take those values up to the chart and see what we've got. So my first point for my t-chart below was 1, 2. My second point was 3, 2. My third point was 2, 2. And those were on our interesting interval between 1 and 3. My next point was 4, 4. And if you notice, now from here to here we look like we have a slope of 2. And if I get beyond 4, the absolute values have no effect on this equation. I would have x plus x, 2x. Well, that makes sense. I'm going to continue with a slope of 2. Take a look between the interval from 1 to 3. Like the value of 2, the absolute values make this the opposite, so I get the opposite of x. The absolute values when x is 2 don't affect this, so that I get opposite of x plus x. They cancel, so it should be constant. And now to the left of 1, I chose 0 and got 4. Let's see what happens. If I'm a value at 0, the absolute values make this the opposite, so I get negative x. The absolute values make this the opposite at 0, I get negative x. So I got negative 2x, slope of negative 2, sure enough. So we have this guy. That wasn't a very straight line, Mr. Hearn. Okay. So x-intercept, we have none. Y-intercept, we have the point 0, 4. Our domain from left to right, the graph's going to go to the left forever, never stops existing, goes to the right forever. Our domain would be interval, negative infinity to infinity. Set builder, the set of all x such that x is a real number. You could do negative infinity less than x less than infinity. Our range starts existing at 2 and does exist at 2 and continues up to infinity. So our range starts at 2, including 2, up to infinity, can't get there. The set of all f of x or y such that y is greater than or equal to 2. Again, that could be f of x. Let's see what we've got so far. Give the domain, give the range in set builder and interval. Rewrite the function in piecewise. Got to do that. List x and y intercepts as coordinate points if they exist. Provide at least 4 quality points. I got 5. We need set builder notation. So as I move from left to right, this graph looks like a line with slope negative 2 and y-intercept 4. So it looks like slope negative 2, y-intercept negative 4, but that only happens until I get to 1. So that happens when x is less than 1. Now you can put less than or equal to here because the graph continues, or you can pick up the equal to part in the next. I'm going to get the less than or equal to here. Then from 1 to 3, the graph just looks like 2. The graph is constant. So it's 2 when 1 is, now this could have been less than or equal to if I'd have used less than here, but now it needs to be less than x. I'm going to go less than or equal to 3. So from 1 to 3, the graph is 2. And then it looks like a line with slope 2. What would our intercept be? Slope 2. That's over 2 down 1, over 2 down 1, over 2 down 1. Looks like that would be negative 4. Double check. Up 2 over 1, up 2 over 1. Yep, it would be right on there. So minus 4. And that would be, what should I use here? Should I use x is greater than 3 or x is greater than or equal to 3? Well, I've already got x equals 3 going to this task A, B, C. It's going to B, so I just want x is strictly greater than 3. So we would say f of x equals, and there's our set builder notation. List x and y intercepts, got them. Provide at least 4 quality points, got it. Okay, graph the function. Actually, a little easier than what we've been doing there. Just graph the function. So this function, it doesn't exist to the left of negative 2. It starts existing at negative 2 to negative 1, continues to exist from negative 1 to 1, and then continues to exist from 1 to 2. So this graph is all confined, and you don't have to have this as part of it, but it's all confined in here. Okay, so from negative 2, we could do this with a t-chart. We could do this by just coming up with lines. I think I'm going to do this with a t-chart. And I'm going to choose negative 2 as a point of interest. So I put negative 2 into this function, and it treats it, if I call this job A, job B, job C. Negative 2 goes in here. I get the opposite of negative 2, 2, minus 2, 0. And so if I get that one on there, I've got negative 2, 0 will go red. Doesn't look red yet, but it will. Okay, now, I can then put negative 1 in, connect the dot, or I can say, well, this is a slope of negative 1. If I put negative 1 in, I'm still on this line. I'm going down 1. Should be right here. But then I stop, and it gets a dot, because I can be equal to. And that's just our straight line there. So now, this one. I'm going to put -1 in here for x, but I'm going to go hunting with a circle. I want to put a circle and not a dot because I can't quite be -1. When I put -1 into here, I get -1. So -1, -1. I would put a circle here. Don't write this down, but let's say -1 gave me 6. I would put a circle up here and start the graph from there. The graph can jump. These piecewise functions often jump. So I'm actually circling this in my head, even though it's already a dot. And then I just look like the graph x, which is up 1 over 1, until I get to 1, including 1. And once again, I'm going to go hunting with a circle. I'm going to put a circle wherever this point comes out. I put 1 in, I get the opposite of 1, -1, +2, 1. So I'm really circling this. And then I have slope -1. Until I get to here, what am I hunting at 2 with, a circle or a dot? A dot. And there's our graph. Okay. If, I guess that's Jonita, invest $1,500 in a retirement account that earns 8% compounded annually. If Jonita invests $1,500 in a retirement account that earns 8% compounded annually, how long will it take this single payment to grow to $5,000? So our amount at time t, we want to end up after some time, $5,000 equals $1,500, what we start with. We're getting 8% compounded every year, so we don't just get 8%. If we went back after 1 year and got 8% of our $1,500 and that the bank said, okay, we're done, we'd wonder what happened to our $15. We also get the $1,500, and I remember that because it's just distributing. I get my $1,500 back and I get another 8%. And now it's just how many years, so t or y. From this point on, this is an exponential function. We're solving for t, so we're going to introduce logarithms at some point. I need to isolate my exponential term first, so I need to divide 1,500. And that gives me, I'm going to start just by dividing both sides by 100. That gives me 50 on 15. I know I can reduce that. Equals 1 plus 0.08 raised to the t. So that is the exponential term is isolated. I can log this. I'm going to ln both sides. If you have an 84 beyond, you can log 1.08, base 1.08 this, log base 8 of 1.08. But I'm going to natural log. So I get ln. That gives me ln, let me reduce this by 5. That's 10/3 equals t times ln 1.08, or t equals ln 10/3 divided by ln 1.08. And that is our exact answer, and I'm going to want to see that. But you might be asked for approximate answer, round your answer to 2 decimals in years. This is years. And then you just go to calculator with this. If you did this log base 1.08, of course it would be log base 1.08 of 10/3. I want to point this out. On these exponential equations, we ought to be able to make some sense out of this. If 8%, if I'm getting 8% a year, in about 10 years, that would be 80% with no compounding. So with compounding, that might be close to doubling in 10 years. So maybe this takes, that would get us to 3,000. I would expect 15, 20 years, something like that. But my point being, if you make a mistake in your calculations on these, you're going to get, generally speaking, you're going to get ridiculous answers. Like it's going to be something like 0.00327 years, and that makes no sense. Or it's going to be 53 million years. I mean, when you make a mistake on an exponential function, generally, and I would say 75-80% of the time, the answer will make absolutely no sense. So take the time, see if it's a reasonable answer. I'll leave the calculator work to you there. Okay, 13, find the domains of f and g. Find the composites f of g, g of f. Give the domain for f of g and g of f. So we want the domain for f. The domain for f, I know that because of the square root, x minus 1 has to be greater than or equal to 0. But I know because I'm dividing, x minus 1, the square root of x minus 1 cannot be 0. Therefore, x cannot be 1. It would survive the square root, but not division. Therefore, x has to be greater than or equal to, excuse me, I just contradicted myself. X has to be greater than 1. Now note, here is set builder notation from that. Therefore, it's the set of all x such that x is greater than 1. Or interval notation, -1, not including, to infinity. In calculus, I would say more times than not we're interested in interval notation, but we need to be familiar with set builder. Domain of G. I can square any number I want. Any number at all I want, I can square it. So this is either all real numbers or -infinity to infinity. So since they don't ask for me to give it in set builder notation here, I'm just going to say domain of G is -infinity to infinity. Then we're to find f of g of x. And I like to think of that as f of g of x because it's really crystal clear to me what's going on here. I need to grab another pen here. I'm just going to work with blue for right now because my pen is dying. F of g of x. That makes it really crystal clear what I'm going to do. I'm going to put x into g, and when I put x into g, I get x squared. So I get f of x squared. And f of g of x, well, f is a factory that takes things, doesn't care what they are, and puts them right here. So that becomes 1 on square root of x squared minus 1. Then I want the domain of f of g. I want the domain of this guy. Well, I go into g first, and I can allow anything into g. Any number can survive through g. And then when I take f of g, I end up with this. I go into g, anything's allowable in g. F of g, I know that x squared minus 1 has to, because of the square root, be bigger than or equal to 0. But because of division, it can't be 0 either. It has to be greater than 0. At that point, I'm going to treat this like an equality, like x squared minus 1 equals 0. So x squared equals 1. X equals plus or minus square root of 1, 1. And let's take a look at our number line here. 1, -1. I'm not allowed to be equal to. It says greater than. So here and here. And then I just test values in each of my ranges. I'm going to start with 0. 0 is located between this time. And 0 gives me square root of -1. That's bad. Bad zone. 2 gives me square root of 3. Not convenient, but that's fine. -2 gives me square root of 3. -2 squared, positive 4 minus 1. So this is a good zone as well. So my domain from left to right, values up to -1, not including -1, or use the union symbol for that, or start at 1 but not quite at 1, start on the other side of 1, up to infinity. Okay, g of f of x. I'm going to come over here because I got a little bit of room. That is g of f of x. I put x into f and I get this. Explicitly tells me it's 1 on square root of x minus 1. And then g of x, g is a factor that takes things, doesn't care what they are, squares them. So I get 1 on square root of x minus 1 squared. And I get 1 on x minus 1. Now, we may fall into the trap. The trap would be here to say, well, x just can't be 1. And if I don't consider the fact that I have to survive my trip through factory f first, that would be correct. But my domain of f, x has to be bigger than 1. I can only have values bigger than 1 and survive my trip through f. So bigger than 1, my domain would be -1 to infinity. So g of f of x, again, follow this. I'll give you a picture here. We're just consolidating the two factories. We aren't reworking anything. They still have to go through all the operations. And if I start with a value of, say, -8 here and put it into f, the factory has to get shut down. Workers have to come in, fix this thing. I can't put -8 through f. I never go to g. So just because -8's okay here doesn't mean it's okay in the process of getting there. It has to run through f first. So we're still limited to -1 to infinity. Okay. Graph the curve. Identify the initial and terminal points, if any. Indicate the direction in which the curve is traced. So here we're going to pick some good values for t. This is parametric equations, of course. So I'm going to choose values for t. I'm going to find values for x and y. And I'm going to work under the assumption we have a little bit of an idea what's going on here with these. Now you can work with a unit circle if you want. Unit circle. Here's the point 1, 0 as we cruise around this circle. Here's the point 0, 1. As we continue around, I get to -1, 0. And as I continue around, I get to 0, -1. And cosine, this tells us that cosine of 0 is 1, and cosine of 90 degrees, or pi on 2 is 0, and cosine of pi is the x values, and cosine of 3/2 pi is 0, and sine of each of these angles, 0 is 0, and sine of pi on 2 is 1. You can do that. Or you can say, I know that the graph of cosine looks like this. At 0, we're up at 1. Grab another red pen here. At 0, we're up at 1. At pi on 2, we're at 0. At pi, we're at -1. At 3/2 pi, I'm back at 0. And at 2 pi, I'm up here. And we can do the same thing for sine. I can say, well, my graph of sine looks like this. So at 0, the sine is 0. Pi on 2, we're up at 1. Pi, we're back to 0. 3/2 pi, -1. And 2 pi, we're back to 0. So values of t. If I choose 0 for t, I get 5 for x. I get 5 times cosine of 0. Cosine of 0 is 1, or cosine of 0 is 1. 5 times 1, 5. 2 times sine. Sine of 0 is 0, or sine of 0 is the y value 0. Either way, 0 times 2, 0. I'm going to continue to just work off the graphs. When I get to pi on 2, cosine is 0. 0 times 5. Sine of 0, or excuse me, sine of pi on 2, 1. 1 times 2, 2. When I get to pi, cosine of pi, -1 times 5. Sine of pi, 0 times 2. 3/2 pi. When I get to 3/2 pi, cosine of 3/2 pi, 0 times 5. Sine of 3/2 pi, -1 times 2. And I expect at 2 pi, putting in 2 pi is the same as putting in 0. I start repeating. So graph the curve, identify. So we're going to graph the curve. We'll start with there. So I need x values to 5 and y values to 2. -1, 2, 3, 4, 5. Y values to 2. Draw this sort of square. My first value is 5, 0. That's not any old point. Does it talk about? That is our initial point right here is 5, 0. From 5, 0, my next point is 0, 2. My next point is -5, 0. And my next point is 0, -2. And hopefully we know enough about these at this point that we know that it is an ellipse. We may come back and talk about that. We've got an ellipse. That's a pretty good one. And I've got an initial point right here. I need a direction of my curve. So right off of the initial point, I put this. So let's see what all we need to do. Indicate the direction of the curve. Got it. Find a Cartesian equation for a curve that contains this. What portion of the graph of the Cartesian equation is traced? Now, we can Cartesian equation this two ways. And I'm going to bring some scratch paper in for part of this. But one way we can Cartesian equation this guy. Cancel that. Hope you didn't. It's going to pop up on my window. I don't know if that comes across on the video or not. One way I can do this is just by looking at the graph and say, well, this is an ellipse. An ellipse is centered at 0, 0. So it's an x squared, plus a y squared on a squared. And a, my x is 5, 25. My y is 2. So 2 squared, 4. So there's my equation. So if you can identify it, great. If not, we have to eliminate the parameter. So for eliminating the parameter, I'm just going to introduce a little scratch paper here. And I'm going to take x and I'm going to solve. I want to ultimately eliminate t. I'm going to divide 5 on both sides and I get x on 5 equals cosine of t. I'm going to divide 2. Y on 2 equals sine of t. Cosine and sine set up nicely to eliminate t. If I square both equations, I get x squared on 25. That looks familiar. Equals cosine squared of t. I get y squared on 4 equals sine squared of t. If I add these two equations together, so x squared on 25 plus y squared on 4 equals cosine squared plus sine squared, but we all know that's 1. So I can get there that way. Okay, and 15, and then we're going to take a break on this one and come back and wrap up the rest of this in another video. So once again, I'm going to, let's see, did I do everything? Find Cartesian equations for the curve. What portion of this is graphed? Well, that is the complete curve. Notice if I would have only been going to pi here, this thing would have stopped right there, and I would just say the part where y is greater than or equal to 0. Or I would say the top half of the ellipse. So this is all of the curve. Okay. All right, number 15. T just strictly less than or equal to 2. And I've got x is 1 plus t and y is square root 4 minus 2t. So I'm going to choose values for t. I'm going to find x. I'm going to find y. I'm going to try to be clever and pick some good values, but most definitely I'm going to put in 2. Now here's a biggie. 2 may not be the initial point. I get it. It's the initial point in my chart, and if this was t is greater than or equal to 2, it would be my initial point in the chart, and it would be my initial point. But I have time units before 2. When t is 1 comes before 2, so this is actually my terminal point. When t is 2, I get x is 3. When t is 2, I get 4 minus 2 times 2, 0, square root of 0, 0. So that is not my terminal, or excuse me, my initial point. It's actually my terminal point. So we have to be careful with direction. So since I have to be less than 2, I'm going to go to 1. Hopefully that works out well. Maybe not great. I get 4 minus 2. I get square root of 2. I guess whoops, that's square root of 2 for the y value. Sorry. When I get 1 for the x value, I get 2. I'll go to 0. 0 looks like a good one. X is 0. 1 plus 0, 1. We get square root of 4. Square root of 4. Good. 2. I guess I'm going to continue on. When I go to negative 1, I get 1 plus negative 1, 0. I get 4 becomes plus 2, square root of 6, not the best. Let's start doing some planning. Will negative 2 give me a good value? Square root of 8. I'll just go with it. Negative 2, don't feel like thinking through it. Negative 1. I get square root of 8 here. And that's not the greatest value in the world, but I know square root of 8 is just a little bit less than 8. But let's get one more good point. I've already used square root of 4 when I got 0 there. I want square root of 9 or square root of 16, something like that. To get 9 in here, I've got 4 minus 2t. I want it to be 9. And I could do this with a rubber stamp, and that gives me negative, if I subtract 9, negative 5, add 2t, I get t equals negative 5 halves. So we might not ordinarily think of that as a good choice. Negative 5 halves. 1 plus negative 5 halves is 2 halves minus 5 halves, negative 3 halves. When I put in negative 5 halves here, I get 4 plus 5, 9, 3. Okay. Again, going to t equals 2. So let's graph those. My x value is positive and negative. My y value is mostly positive, maybe all positive. We'll see. So for my purposes, I need y values up to 3. I need x over 1, 2, 3, and I need them to be to the left 1.5. So that should do it for us. Okay, let's put some of those on here. So careful, I've done this lots of times. Cover up t. I'm graphing these points, 3, 0. I'm graphing 2, square root of 2, about 1.4. I'm graphing 1, 2. I'm graphing 0, root 6. Well, it's a little bit more than 2. It's between 2 and 3. Approximation here. Negative 1, I'm almost up to 3. And at negative 1.5, I am up to 3. So I have a curve that looks like this, and it does stand to reason. We've got a square root function here on y. It does kind of stand to reason. Imagine if I squared both of these, I would end up with a parabolic curve. So I do not have an initial point, and my direction, I know I'm graphing it this way, but when t is small, I'm over on this portion of the graph. My direction of the curve is here, and it just slams into there. Okay, so identify the initial and terminal point. This is terminal point. Terminal point is 3, 0. Initial point, there is none. My terminal point back on this problem, there was one. Terminal point, because when I put in 2 pi, I would get the same thing, is also 5, 0. Forgot that. Got to be careful. I do too. So now let's eliminate a parameter. I'm going to go ahead and eliminate the parameter by solving this equation for t, and I get x minus 1 equals t. So if I take that value of t and put it right here, I get y equals the square root of 4 minus 2 times x minus 1. So I get y equals, let's see, that would be a negative 2x, and I would get a plus 2, I get plus 6. You might even want to think of that as y equals square root of negative 2 times x minus 3. You don't have to do that. Either one of those would be good. What portion of the curve are we dealing with? Well, this would be a logarithmic function, and plain old log x looks like this, but it's to the right 3, got it, and it's backwards, and everything happens twice as fast, and that seems reasonable to me, and it is the entire curve. So entire curve. Now when you take the test, there will be lines provided to put all of these solutions in. Okay, as I said, we're gonna wrap this up. We're going to pick up from here on the next video. Thanks for joining me. We got a lot of things to do, and we got to be pretty efficient at them because you're going to do those in 2 class periods.